Let's talk about differential equations and how many solutions we should expect. First things first, in a differential equation, your answer is actually a function. For instance, the first one we often see is this one up here, which says I want a function so that if I take the derivative of it, I get exactly the same thing I started with. In calculus, you learn exactly one function that's equal to its own derivative, that's e to the x. But also, I fibbed a little bit because that times any constant will still be its own derivative. For instance, 2 times e to the x is its own derivative. By the way, the equation y prime equals y is called first order because we took one derivative in that equation. Let's see an example of a third order differential equation. Perhaps something like, hey, take 3 derivatives and wind up with this 0 function. Well, if you think for a while, what could I take 3 derivatives of so that I get left with nothing? And actually the power rule comes to mind. For instance, if you start with something like, I don't know, x squared plus 3x minus 17, if you take 3 derivatives, the powers are going to get lower and eventually you'll be left with nothing. In fact, you've probably noticed that those numbers don't really matter, and you could have anything of the form ax squared plus bx plus c, and that would definitely be a solution to that differential equation. Because we had a third derivative in that one, that's a third order differential equation, and it's no coincidence that we had a 3-dimensional space of solutions. We had 3 parameters to choose for a, b, and c. In general, if you have a differential equation, and let's just assume that all the coefficients are constant, so something like this, if you solve it, the solution space will always have dimension that's equal to the order of it. In other words, the highest derivative that you ever take. To prove this, we actually have to do 2 separate things. First, we have to demonstrate that there are at least that many different independent functions that satisfy the equation. We can do this in a number of ways. One way is if we have an order n equation, we can attach that to an order n polynomial or a degree n polynomial. That will have n roots counting multiplicities in the complex numbers. To those roots, we can cook up independent functions and show that they satisfy the differential equation. And, by the way, all of these types of equations have the property that if I add 2 functions that are solutions, or I scalar multiply them, or do, in general, a linear combination, those are still going to be solutions. So that shows that if we have something that's order n, then we do have at least an n-dimensional vector space of solutions, and now we just have to show that there can't be any more. To do that, there are different ways to proceed, but the main way is to look at Taylor series. And so if you think about it, because you know this equation is true, your function, say in this example, not only has 3 derivatives, it actually has to have 4, right? Because if you think about it, y triple prime is equal to this thing over here, and that must mean that I can take another derivative because everything over here must have derivatives as well. And so that basically means that in these differential equations, we have infinitely many derivatives, and so we can talk about Taylor series. Now, if you take the differential equation and you use that information to figure out what is happening with all of the coefficients, I did one example up here. Pause the video and see what's going on. You're going to see that basically all of those coefficients are determined from the first several, and that several is exactly the order of the differential equation. For instance, here you can see that I only need to know what a0 and a1 are, because after that I get all of the other information from the differential equation. And so at the end we still have some freedom, but that freedom is exactly equal to the order of our differential equation. That's basically a complete proof. There are a few things that you would have to be careful with. I should say that a much stronger version of this theorem is true. If you want to Google Wikipedia, I think Googling for existence and uniqueness of differential equations, you'll get the best statement you can. Also, if you like this content, especially the more theoretical parts of it, let me know in the comments and let me know what you'd like to see.